In this video, I will be talking about polynomial functions of higher degree. Previously, we learned about quadratic functions, which are the functions that have the degree 2, because they're always raised by a power of 2. So some of the objectives of this lesson are using transformations to sketch graphs of polynomial functions, using the leading coefficient test to determine the end behavior of graphs of polynomials, and find and use the real zeros of polynomial functions as sketching aids. Now we're going to talk a little bit about graphs of polynomial functions. Again, polynomial is an umbrella term for functions that looks like a of n x to the n plus a sub n minus 1 x to the n minus 1 plus going in a similar direction, looking like a sub 2 x squared plus a sub 1x plus a sub 0. So these are the types of functions when we say polynomials. And depending on the degree n, the function looks different. If n is 2, then we call it a polynomial function. And then in this chapter, we're going to talk a little bit about more general functions, so functions that have higher degrees of n. So n is going to be bigger than 2. First feature we need to know about these polynomials is that polynomial functions are always continuous. So what we mean by continuous is that the graphs of polynomials have no breaks, holes, or gaps. They're always consistent. They're always continuous. You're not going to see any break, any holes, any graphs. In other words, you draw a curve without moving your pen up. So it's always consistent. Here's an example of a graph that is not continuous. As you can see, there's a gap between this first curve and the second curve. So that's why this function is not a polynomial. It's not continuous. The second feature of polynomials is that they only have smooth, rounded turns, as you can see in the first image. So here, one turn, there's another turn right here, there's one here, there's one right there. We generally call these turns something like a turning point. So some language here, we generally call them turning points. And this function has 1, 2, 3, 4 turning points. As you can see, they're always smooth, they're always rounded. Another thing we need to know is a polynomial function cannot have a sharp turn. So as you can remember, this is the graph of the absolute value function. And as you can see, it has a sharp turn at 0, 0. So that's why this guy is not a polynomial. Polynomial functions generally don't have a sharp turn. All right, so we're going to move on to our next concept here. So we're going to take a look at some examples of functions. So on the left graph, you're given x squared and x to the 4th. On the right-hand side, you have x cubed and then x to the 5th. So the general idea here is when n, the exponent, the highest exponent, is even, then the graph is going to look like this parabola on the left. It's always going to touch the x-axis and it's going to have an x-intercept. Whenever n is odd, the exponent is odd, it's going to pass through the x-axis and then it's going to have an x-intercept right at that point. Next, we're going to take a look at an example of how to sketch polynomials, monomial functions specifically. So when we say monomial, these are the ones that only has terms like x squared or like g of x equals negative x to the 7th. Like they're only going to have one x term. So the one in part A, you guys realize it's f of x equals negative x to the 5th. So you guys realize n, the degree is 5, which seems to be an odd number. So that's why the graph of this guy is going to look like the ones that we previously see, like x cubed or x to the fifth. And so, but the thing is, because it's negative, it's going to be reflected about the y-axis, and it's going to look like this. So you guys realize the negative coefficient, or the negative x being multiplied, is reflecting it by the y-axis. So the second function is, because n is 4, which is an even number, it's going to look like a parabola, but because we're adding 1 to the x, it's going to shift to the left side. So we previously talked about transformations, and that's what we're using here, our transformation knowledge. Because we're adding 1 to the input, it's going to make the function shift to the left exactly 1 unit. And as you can see here, because this is a fourth degree polynomial, it's going to open up, and then because we're adding 1, we have to shift the function to 1 unit to the left side. So that's why it looks like this. So transformations are extremely useful for us to make sense of graphs and then possibly sketching them. So the thing here is that we sometimes realize that endpoints of graphs or parabolas sometimes act different. So the way we handle that is we use this test called the leading coefficient test. And so what this does is that this helps you determine the endpoint behavior of functions. So the test goes as the following. As x moves without bound to the left or right, the graph of the polynomial function, this is a generic formula for a polynomial function, eventually rises or falls in the following manner. So two conditions for that. One, if n is odd, meaning the degree of the polynomial is odd, then two scenarios happen. If the leading coefficient, which is a sub n, you may remember, so that the coefficient of the highest x, a sub n. So if a sub n is positive, then it's going to fall down on the left side, and then it's going to raise on the right side. But if a sub n is negative, in other words, the highest leading coefficient, is negative, then it's going to raise up on the left and then falls on the right. So those are the two things when n is odd. So we have to keep that in mind. For when n is even, then if the leading coefficient is positive, then it's going to open up. And this is something you may remember from parabolas. Remember, with the parabolas, if a is positive, then it opens up. If a is negative, it opens down. So similar idea here for polynomials that have higher degree, because n is generally going to be bigger than 2. Depending on the leading coefficient, we can know what's going on the end points. So if a sub n is positive, then it's going to open up in both sides. It's going to raise on both sides. If a sub n is a negative number, then on both end points, as you can see, the function, the polynomial, will fall. So here are some of the examples. So let's take a look at the first function. So you guys realize the degree of this polynomial is 3, which is an odd number. And then let's determine the leading coefficient. So again, the leading coefficient is always the coefficient of the x that has the highest exponent or degree. So in this case, it's going to be the x cubed term, but the coefficient for this term is going to be -1 because that guy has negative in front. So a sub n in this case is a -1. And you guys realize a sub n, which happens to be -1, is a negative number. So it's smaller than 0. So according to the leading coefficient test, so the leading coefficient test says if n is odd, the degree, and then if the leading coefficient is negative, then it's going to raise on left, and it's going to fall on right. So according to the test, we make the conclusion that the function is going to raise on the left and then fall on the right. So roughly speaking, it's going to look like something like this. So the function is going to go something like this. So it's gonna raise on the left, fall on the right. On the next page, I probably have the exact situation here. As you can see, the function looks like this. So the second equation, so let's take a look at the second example. You guys realize n in this case, which is the highest exponent, is 4, which is even. And then let's take a look at the leading coefficient, a sub n. So we look at the x to the 4th term, which has 1, because it's like 1 times x to the 4th. And then this guy is positive, right? So a sub n is positive here. So then according to the leading coefficient test says if number's even, and then if a sub n is positive, then it's gonna raise on both ends, right? So the function is gonna look like, because this is a 4th degree polynomial, it's gonna be raising on the left, and then something is gonna happen in between, and then eventually it's gonna start raising up again. So I don't exactly know how the function looks like in between, but on both ends, the function is gonna raise. So lastly, let's take a look at this guy. So this guy has n being 5, which is an odd number, and then a sub n, which is 1, which is positive. So if n is odd and then a sub n is positive, according to the leading coefficient test, the function must fall on left and then raise on the right. So in the next few slides, you can actually see that what we found is true when we actually graph the functions. All right, so next thing we're gonna do is, now that we learn how to find the end, like the characteristics of the endpoints of these polynomials, now the question here is, what about in the middle? So in other words, like when we determined with the leading coefficient test, like say we know that this polynomial raises on the left, it does things sometime like somewhere in the middle that we don't know, and then it goes this way. So the question you may have is, how do we determine what's going on in between? Like, how do we know what the function does in between these endpoints? So the leading coefficient test only tells you, the endpoints. But how do we figure out what's going on in between? Like where does the function go? Because there's multiple scenarios. Like sometimes the functions go like this green line, they're just like passing through and then like doing this, and sometimes it does what I showed you with the purple dots, like it might do something like this. There could be other scenarios. It could be like, you know, going like this, maybe pass like this. We don't know what's going on in between. So the way we can determine what's going on in between is that we use the real zeros of polynomial functions. In other words, we find zeros. So if we know zeros, then we can know what the function does. The reason for that is, as you can imagine, zeros are the points where the function crosses the x-axis. So that's why these are really useful. So for instance, for that red curve, the zeros are these points. If I knew these points, then I can say, well, the function must raise on the left, but it has to pass through that black dot, and then it has to go down to the negative side, and then hang out there a little bit, and then come back to that other dot, which is right here on the right-hand side, and then it should continue growing up. So same thing for that green line. You guys realize green line has 2 zeros, in other words, 2 points where it's gonna cross the x-axis. And then we have to be able to find those points so that we'll know how the function behaves in between. So the way we can determine what's going on in between for the graph, we're gonna find those zeros of polynomials. So before we talk about how to find zeros, here's a couple of things we need to know. So if a polynomial function, generic polynomial function, has a degree n, then the following statements are true. So the function f has at most n real zeros. So for instance, if you're given a quadratic function, so like say f of x equals ax to the n, to the square specifically, let me go back, okay, ax squared plus bx plus c, you guys realize this one has the degree 2 because it's a quadratic function. This has at most 2 zeros. So this is a useful information. What that means is that this function might have 1 0, it may not have a 0, and it may have 2 zeros. So depending on the quadratic function, you have different interpretations. So let's have another example. If you have f of x, or let's make this to be g. So if you have g of x equals something like ax to the fifth plus bx to the fourth plus cx to the third plus dx squared plus e. So let's say this is my fifth degree polynomial because the n is 5, you guys realize. So this guy has at most 5 zeros. So this function will cross the axis at most 5 times. It may not do 5 times all the time because it depends on what these a, b, c, d, e numbers are, but it may have at most 5, and then it might have 3, it might have 4, so we don't exactly know, but it may have different ones. So we're going to keep in mind that a polynomial function in general, at most have n many zeros. Another thing we need to keep in mind that the graphs of functions will have n minus 1 at most turning points. So you guys may remember the turning point idea I told you earlier. So like say if you have a cubic function, you may have something like this, right? So you guys realize this is a cubic function, so it's something like f of x equals ax cubed. So the cubic function will have at most 1 and 2 turning points. So it will have at most 2 turning points. So we're going to keep those two features in mind for polynomial functions. There's a strong interplay between graphical and algebraic approaches to this problem. So generally speaking, when we say real zeros of polynomials, we say different things, different language, but essentially they're all conveying the similar message. So when we say x equals a is a 0, or we might say x equals a is a solution to the equation f of x equals 0, x minus a is a factor of the polynomial. So this is useful. You may remember we had the factored form for polynomial or quadratics. It looks like something like this. You may remember a times x minus x1 times x minus x2. You guys realize what I call these x's, so x1 and x2 are zeros. So factored form gives you these factors, x minus x1 and then x minus x2. So these guys are factors. So that's why this a, in this case, a is the solution. So it's just a different way of saying it. And then another interpretation, of course, I told you before, zeros are the x-intercepts. So zeros are where functions crosses the x-axis. So that's why we can have this notation where we say a comma 0 is the x-intercept. So all these statements are basically equivalent. They convey a similar message. All right, so we take a look at this example. Find all the zeros of f of x equals 2x to the fourth plus 2x squared. So then determine maximum possible number of turning points and the graph of the function. So let's do that first. So what's the degree of this polynomial? So when we say degree, we mean n, and n is always the highest exponent of an x term. So the x term we have is negative 2x to the fourth and then 2x squared. The highest one is 4. So the degree is 4. So the possible number of turning points and the zero. So we may have at most 4 zeros, and then we may have at most 3, because it's n minus 1, turning points. So we're going to keep in mind that we're going to have at most 3 turning points. All right, so let's take a look at zeros. How do we find the zeros? So the way we find zeros is we always set them equal to 0. And then generally we factor. So then here we factor out the negative 2x squared, because you guys realize this one has 2x squared and this one is already 2x squared. And so that's why we factor that out. We can factor out the negative, it doesn't matter. We could have kept as a positive. So then negative 2x squared times x squared minus 1, because when you distribute this guy, you will get negative 4x to the fourth, or sorry, negative 2x to the fourth, plus you'll get 2x squared. So you'll get the function back. So this is very useful because we will be able to factor out. So x squared minus 1 can be factored out as x minus 1 times x plus 1. The way we do that is, you guys may remember the difference of squares from algebra. So difference of squares is something like when you have a squared minus b squared, you can always rewrite it or factor as a minus b times a plus b. So you're going to remember to do that, because here I got x squared minus 1 squared, which looks like a squared minus b squared. So that's what we did. So after doing that, we ended up having negative 2x squared times x minus 1 times x plus 1 equals 0. So the question is, how can I make the left side to be 0? Possibilities are this guy is 0, or this other factor is 0, so x minus 1 could be 0, or that last factor, x plus 1, could be 0. So there are 3 possibilities. So for each possibility, we solve it. So we say, well, what if negative, let me use purple to be consistent. If negative 2x squared is 0, then x has to be 0. So that's 1, 0. The second scenario, what if x minus 1 is 0? In that case, x is 1. The last scenario, what if x plus 1 is 0? In that case, you get x equals negative 1. So that's why x equals 0, x equals 1, and x equals negative 1 are my zeros. So at the beginning, I said we will have at most 3 zeros, and you guys realize we actually find 3. Sorry, I said at most 4 zeros and then 3 turning points, and then we will have 3 zeros for this guy. It's not going to have 4. So the graph of this guy actually looks like this. So you guys realize the zeros that we just found are right here, negative 1, 0, and positive 1. So these are the points where the function crosses the x-axis. And then you guys realize you have 1, 2, and 3 turning points. So again, using the idea of zeros and turning points, we can determine what the function does. And then by the leading coefficient theorem, we can say what's going on the endpoints. So because this guy has the degree 4, which is even, and because the leading coefficient is negative, because it's negative 2, so then we can say, well, this guy should fall on both ends. That's what the theorem says. And then we confirm that on the graph. You guys realize the function falls on both sides of the graph. Sometimes we have this idea called repeated zeros. So if a function has x minus a raised by k, where k yields a repeated 0, x equals a, of multiplicity of k. So if k is odd, then the graph crosses the x-axis. When k is even, then the graph touches the x-axis. So what I mean by that is you may have situations where the function looks like this, like factored form. So like say a times x minus 1 times x minus 1 times x plus 1, right? You may have situations like these. Or you may have something like g of x equals b times x plus 2, x plus 2, x plus 2, and then x minus 7, right? So you may have situations like these where you may have repeated factors. So you guys realize this guy is repeated. So what I can say is then this function is the same thing as a times x minus 1 squared times x plus 1, right? Or the second one, the second function could be written as, so this guy could be written as b times x plus 2 because we have the 3 over, so x plus 2 cubed times x minus 7. So that's when we have repeated zeros, because you guys will realize that for the first one, x equals 1 is a 0, but it's repeating. For the second scenario, you guys realize x plus 2 is cubed, meaning x equals -3 is a 0 for this, oh sorry, -2 is a 0 for this guy, but it's being repeated. And then that tells you what the graph does. So if k is odd, so if it repeats 3 times, then the graph crosses the x-axis at that point. So it should cross x equals -2. But if k is even, if the exponent is even, like in the first case for f of x, you guys realize x minus 1 repeats. So at that point, at x equals 1, the function should touch the x-axis, right? It should kind of like bounce off at x equals a. So the graph will bounce off at that exact point. So in the first graph, f of x, the f of x, the function, will bounce off at x equals 1. So that's how this idea of repeated zeros is useful. It tells you whether it crosses the x-axis or bounces off at the x-axis. So in the slide, you can find some information about like what I just verbally said. Again, to graph polynomials, you use the fact that the polynomial function can change signs only at its zeros. We know that is true because you guys realize if you have a function like this, at the zeros, at these points, the function goes from positive to the negative side. And then on the second one, it's at the negative side, but now it's at the positive side. So it changes the signs at its zeros. Between two consecutive zeros, a polynomial must be entirely positive or entirely negative. So you guys realize with that first graph, you guys realize in between these points, in between the zeros, the function is always negative. But if you had something like, let me draw another example. Let me have like 3. So you guys realize, so let's call this x1, let's call this x2, let's call this x3. So in between x1 and x2, the function is positive. Between x2 and x3, the function is negative. Okay, so last thing I need to say is the resulting intervals are test intervals in which you can choose a representative x value to determine whether the value of the polynomial function is positive or negative. I'm going to talk a little bit about that in class, but what it essentially means is that if you pick a point, like say right here, so like let's call this x5, if you pull that point and put it into the function, and if the function is positive, then the function in that interval has to be positive in that whole interval. But if you pick something like here, if I'm going to pick x6, and if I put that into the equation or the function, and then if I got something negative, what that means is that in between x2 and x3 in this interval, the function is always negative. So you test using these points, and then we call these intervals to be test intervals. And these intervals are found always in between points or always in between zeros of these functions. So yeah, what we learned always is useful for graphing any type of polynomial. So this is like a general things that we need to know about polynomials.